Chapter 7. This is the only material that'll be on exam 5. And we're going to talk about atomic structure. That is, how are atoms built? How do we make an atom? And then use that information to get a better understanding of how the periodic table is structured. Because the periodic table isn't built that way just for looks. It's built that way for a reason. And when we study the structure of the atom, that gives us a clue as to why things are where they are in the periodic table and how we can use it. We can use the periodic table to help us build atoms. All right, so here we go. First, we're going to start off with trying to wrap our minds around the concept of light. And another term for that is electromagnetic radiation. We get an indication of differences in light and the information that you can get from them by just looking at fireworks. I mean, how do they get those different colors? Some colors are easier to make than others. Like yellows and oranges, they're really easy to make. Blues are really difficult to make. So if you see blue in a firework, you go over to whoever built the fireworks and shake their hand because they did a good job. All right, let's see. Oops. It's not supposed to do that, I don't think. Well, I guess it is. I thought I had more on that slide. Okay, some of the questions that we consider besides why do we get those different colors, that's good information. What do the colors mean? Because they carry information with them. Why do different chemicals make different colors? Right? So what's the relationship between the chemical and the color it makes when we add heat to it? And those flames are examples. Different elements make those different colors. When I was working in the federal government, we'd have tours come through, usually young school children. So I had this one machine where I could aspirate solutions through it into a flame. And the flame would heat up the elements that were in the solution, and you get different colors from them. And the one the students liked the best was strontium. Strontium is an alkaline earth, and when you heat it up in this flame, you get hot pink. They like that one a lot. There's also a difference between how the chemical shows colors, not just with heat, but with environment. Right? And you get different colors with different environments. We noticed when we had when we did our lab with copper sulfate, when it had water in it, it was a blue color. When it didn't have water in it, it was white. And when you put white copper sulfate and hydrogen, no water, into a solution of water, it instantly turns blue. So water has something to do with it. Why are some colors common to different chemicals? What is it that distinguishes the color from strontium as hot pink and the color for sodium as bright yellow? I'll give you a hint. It has to do with the electrons. We've got examples that we can point to in nature. One of them is our own red blood. You know, why is blood red? When it comes from an artery, it's bright red. And when it comes from a vein, it's either dark red or slightly purple. until it sits in the air for a while, and then it turns red again. That has to do with the presence of oxygen or the absence of oxygen. If you got oxygen present, you get that bright red color. If oxygen's missing, like in venous blood, then you get the slightly purplish color. And that's due to the association of oxygen with iron in the molecules, hemoglobin. We won't go into a lot of detail there. It's just the point is when iron is associated with oxygen, it's one color. When it's not, it's a different color. Research that I did on my master's degree was with crawfish. Right? I was working down in Louisiana, and I had to do research with crawfish processing waste. The various fishermen or crawfish farmers would bring their products to a processing center and sell it to them. And then the processing center would cook the crawfish, and then they'd extract the tail meat and package it up, freeze it, and send it all over the world. Well, that's a lot of waste, because the crawfish tail meat is only 15% of the crawfish mass. They've got 85% of that weight is waste. So these companies were desperate to find out what to do with it. What could we do with it that would mitigate our waste problem? And one of those has to do with the red color in the shell. When you cook a crawfish, well, they're slightly red when they start with, but when you get finished cooking them, they're bright red. And I found that one of the primary chemicals that cause that red color was this astaxanthin. You can see the formula down there at the bottom of the page. It's a long chain, and it has alternating double bonds with single bonds. Well, we'll talk about that probably, well, maybe later in this course, but definitely in the second course. That when you get these alternating double and single bonds, that's what's called conjugation. And you spread the electron density out over a large area, which decreases its energy level. So when you decrease the energy level from the blue end, we'll talk about that in a minute also, to the red end, the more of these you have, the closer you get to red. And you can see these carotenoid chemicals in various types of plants and animals. They come in different shades of reds and oranges, primarily. Okay. So the answer to all these questions, why do you get these differences under different conditions and different molecular structures? And the answer is light. Electromagnetic radiation explains the colors. What we want to know is why do we get that difference in electromagnetic radiation? Right? It has something to do with the molecules, something to do with the atoms and the electron shifts that occur in those atoms. So let's talk about light in particular. Electromagnetic radiation. We can characterize light with three values. One is wavelength. Right? I'll write it out first. We use a symbol for wavelength. It's the small letter, the Greek letter, lambda. Like that. That stands for wavelength. Frequency is the letter nu, N-U, and it kind of looks like a V, but it's not really. It's a small letter, nu, from the Greek language, and then speed, or sometimes velocity, we say. It should be velocity because once light gets going, it doesn't change until it hits something, and then that moves it. But its speed, we give the small letter c. Okay. So what are the units of measure for each one of these? Well, in standard SI units, the wavelength is in meters. Now, there are other expressions, but that's the SI unit for meters. And it is the distance between two wave crests, because you can represent light on a chart like this is like that, right? And the wavelength is the distance between two of these crests. Okay, it's not between this crest and that trough, it's between these two crests. All right, frequency says, all right, if I've got my eyes fixed on, say, this position right here, you know, I'm watching that position right there. How many of those wavelengths pass that position in 1 second? So this would be cycles, meaning how many wavelengths pass my eye in 1 second. Okay? And speed, of course, is simple. I mean, we've used that forever. Meters per second. Okay? Now, cycles is not a dimension. It's an expression of what's happening. So actually, the unit of measure for frequency is reciprocal seconds. It's just seconds to the -1. So let me see. I think I'm stealing my thunder. Let me go to the next slide. Here we go. All right. So if we put these together, I mean, if we just use dimensional analysis, what would happen if we multiplied this one times that one? And let me do better than that. That looks too much like a gamma. There we go. Well, this one would be meters, and this one would be reciprocal seconds. So the units of measure here would be meters per second, right? Which is the speed of light. So there's our first formula having to do with light. Speed of light equals its wavelength times its frequency. And of course, these units have to be the correct units if you want this to work out, right? Meters, seconds, meters, seconds. Right? If you have a different value for wavelength, you got to convert it to meters before it'll come out as meters per second. Now, in a vacuum, that value for C is 2.9979. That's where I usually stop. 10 to the 8th meters per second. That's how fast light moves in a vacuum. Now, when it has to interact with other materials, like it goes through a glass of water, or it goes through a diamond or some other material, then it changes its speed. But that's another topic. This is the speed of light in a vacuum, and it's pretty close to that in air. If it passes through a gas, most gases don't slow it down that much. So we're going to use this value for light traveling through air or a vacuum or almost any gas. All right, so there's a representation of a wave. Right. Notice the top one, the wavelength is very large. And the middle one, the wavelength gets shorter, and the bottom one, it gets even shorter still. Okay, so what happens in relationships of wavelength to frequency? Remember when we had gas laws, pressure times volume equals a constant. That is a constant. Speed of light is considered a constant. So if we have that times that, these are variables, and multiply them, their products equals a constant, then what did we get here? Well, if we graphed it out, we got a hyperbola. But the point is, they're related to one another. They're inversely proportional. If this one goes up, that one has to go down. So if wavelength gets smaller, if this one goes down, frequency goes up. Okay, so that's what they're trying to show here. Notice the top one. The wavelength is that wide. And it's 4 hertz. Actually, I didn't mention that before. Hertz is equal to cycles per second. Okay. We wanted to honor a scientist who was working in this area and produced a lot of most of the advances at a certain position time period, advances in study of light. So we named this unit after Hertz. So when it says Hertz, it means cycles per second. All right, so if it's 4 Hertz at that wavelength, but now the wavelength is cut in half, it's decreased by half, then we should double the frequency. And that's what happens. When we go from wavelength 1 to wavelength 2, the frequency doubles from 4 to 8. And then when we go from wavelength 2 to wavelength 3, we're decreasing the wavelength in half again. So now we want to double the frequency from 8 Hertz to 16 Hertz. They're inversely proportional. All right. So let me make room here. We can put this up on the board again if we need it. This slide is showing you the electromagnetic spectrum. And in this particular version, we're going, wavelengths are increasing in size from left to right. So on this spectrum, wavelength here is increasing. Right? If wavelength increases, what happens to frequency? Frequency should decrease. So frequency is increasing this way, decreasing that way, right? They're inversely proportional, so they move in opposite directions. There's a sliver, a very narrow band right in the middle for visible light. Right? That's where we can actually detect it. And we say visible because science is anthropocentric, right? It's man-based. So visible is visible to us, right? We've discovered animals and even plants that respond to the spectrum on either side of the visible spectrum. But the visible light, right? If you had any science at all, even in grade school, right? What's the order here? Right? How do you name the colors of the rainbow? Right? Everybody remembers this one. Right? Red, orange, yellow, green, blue, indigo, violet. Roger Bibb. Only this should be going the other direction, the way we've drawn it. Because the longer wavelength is associated with red. So it's red on this side and violet on this side. Okay? Longer wavelengths are toward the red. Shorter wavelengths are toward the violet. Conversely, the lower frequencies will be red and the higher frequencies will be violet. Now, I'm going to put something else up here because I think it's important to understand. As we go, we're going to get a slide on it in a minute, but as we go from lower frequencies to higher frequencies, energy also increases. The energy of that light is directly proportional to the frequency. Okay, so we can divide the spectrum up and we get a region here on this side of violet called ultraviolet. Okay, now they're giving you the wavelengths there in meters, and I'll do that in just a second. But on this side is infrared. So when you go to a restaurant and they have your food sitting under those lamps that look kind of reddish when they're turned on, those are infrared lamps. These are often called heat waves, right? The infrared. Ultraviolet are the burn waves. When you get out in the sun on a hot summer day and you're at the beach and you're trying to soak up some sun, These are the ones that damage your skin and cause a tan. Tanning is simply your skin's response to damage. So when you damage your skin, it tries to create more melanin to absorb incoming radiation. It can't do it really quick. Right? So more often than not, if you stay out there long enough, you're going to burn before you have enough melanin to block the radiation. Okay, so as the wavelength gets longer, we move to an area called microwaves. And then even longer, we get radio waves. And that's right. This is the part of the spectrum that we use to communicate over AM and FM radio and shortwave radio also. So AM is the longest ones, shortwave is in the middle, and FM is on this end. Okay, now we go the other direction. As the wavelength gets shorter and shorter, then we go from ultraviolet to X-rays. And those are the ones that the dentist and the doctors, they fire through your body to see what's wrong internally. Then we get to gamma rays, X-rays, gamma rays. And there's a Greek letter that I use for gamma. I'll write it in first. Gamma rays. The Greek letter for gamma is, it's too much like that. Gamma rays. So these are very, very high energy. If you pay attention to the popular media, occasionally they'll mention something astronomical like gamma ray burst. A gamma ray burst is a directional gamma ray that comes from a star when it does certain things. We won't go into that now, but they're very, very high energy and they're focused in a direction. And that's really good for us because if it's not aimed at us, then we don't have to worry. But these things can come from thousands of light years away. And they're so powerful that if one of them is directed at Earth, it just by accident, it happens to hit Earth, then it could strip away our atmosphere in just minutes. So very, very high energy. Okay, there's your electromagnetic spectrum. Points to take here. Well, first of all, they got it in meters, right? Wavelength in meters. And that's true, right? But there are other units of measure that are more useful sometimes for us. One is nanometers. Right? What's a nanometer? It's 10 to the minus 9th meters. And when you get these values that are like 10 to the 7th, right? 10 to the 7th, 10 to the 8th, or 10 to the minus 7th, 10 to the minus 8th, then nano is a useful tool here. Right? The visible spectrum, red is in the neighborhood of 700 nanometers, and the blue end of the spectrum, the violet end, is in the neighborhood of 400 nanometers. So 400 to 700 nanometers is the visible range. Now, is that true? I mean, is that correct for 10 to the minus 7th meters? Well, let's see. Let's take 400 nanometers. What do I say to do? Take that part right there and say, what does that mean? That means 10 to the minus 9th times 400. So change this one times 10 squared times 10 to the minus 9. Okay, there you go. We can do that. Right? This one becomes this one. Well, this is squared. What do you do when it's the same base to different powers? You just add them. All right, so 2 minus 7 is 10 to the minus 7. So 4 times 10 to the minus 7th is 400 nanometers, and there it is right there on your chart. Now, when you get to radio waves, meters are a good choice. 10 squared meters, right, 100 meters, or 10 to the 4th would be 10,000 meters. But usually when you tune your radio, you're not looking at meters, you're looking at frequency. Right? It says how many hertz, what's the frequency. Right? One station I listen to is 101.1. Right? That's see, FM be megahertz. All right, we'll do some calculations with these afterwards. Just recognize that when you're going this way, wavelength is getting bigger. When you're going this way, wavelength is smaller. And when you're going this way, frequency is increasing, frequency is decreasing in that way. And together with the frequency, energy goes up with increasing frequency and down with decreasing frequency. All right. Believe me, this is going to be useful information for trying to figure out how atoms work. When you stop and think about it, we mentioned astronomy just a minute ago. Let's see. Yeah, we mentioned astronomy a minute ago, and be sure I didn't miss anybody. Yeah. Oh, Kathy's here. I didn't hear you ding in. Okay. How do astronomers get their information? Right. Well, up until recently, the only way that we could explore the rest of the universe was with telescopes, right? And their currency is light. Light comes to us through the telescopes. We do things with it, right? We can see different colors of stars, but we can also now take that light and run it through instruments that split the light apart and look at the different colors that it has. In fact, we can measure them in terms of their frequency or their wavelength, whichever the case may be, and deduce things about what's out there. So information that comes to us about the atoms and molecules that are out there come to us from light. So we need to know how do they produce that light, because if we know how they make the light, if this element makes a different color than that element, then we can tell what elements are out there. So that's where we're headed. There is a relationship between light and energy, right? And this poor little pickle is being energized by a direct current. I'm not sure what it's from. Is it from just a plug in the wall, or is it from a battery, or what the case may be? That electricity is converting its energy into heat and light, because that pickle is cooking, I guarantee it. Okay. We got an understanding of what light is and how to interpret electromagnetic radiation. First, from the equations of James Clerk Maxwell. This is in about the middle 1800s. And his equations were based upon the understanding that light is a wave, just like we've drawn it. And his equations worked. I mean, they answered questions. And they're still valid today, as long as we treat light as a wave. And this is coming up, there are certain things, behaviors about light and its interaction with matter that can't be explained with waves. Right? So in those cases, Maxwell's equations don't work. All right, so at this point, all through the 19th century, until we came up well into the 20th century, about a decade or so, scientists believed that they had a pretty good understanding of how the universe worked. And all they needed to do now was to refine their theories. Well, it wouldn't be long before they were proven wrong. Right? We really didn't know how the universe worked. And now we're going to get to the point where we have to understand light in terms of not just waves. Light is a wave, but light can also be described as a particle. It can be considered something with mass, something with velocity as a particle, not just the velocity of a light beam, but as a particle, how it behaves. Some of those indications came from Max Planck. He was working on black body radiation. Now, what is black body radiation? Black body radiation is a black body is a mass that does not produce any of its own light. Right? No chemical reactions. It has no energy of its own. So the only way that it can produce light is if it's heated up. If we add energy to it, then it will start to radiate light. And in fact, that's how we know the temperature of stars on their surface, right? We look at the radiation that's coming from them, and the bluer it is, the higher its temperature. Okay, so Planck was also working on this relationship between frequency and energy that I put in our chart before. As frequency increases, energy increases. And this is where I got it. This is Planck's equation. The energy of light is equal to some constant. This is Planck's constant. Did I spell that right? No, it has a C in it. Planck's constant. And you don't have to memorize the value for this constant. It's in useful information. Planck's constant times the frequency of the light. And you can calculate how much energy that light has. Well, it's kind of hard to wrap your brain around the energy of light if it's a continuous wave. Like how much energy does it deliver, right? When that light is passing, going from here to there, right? As long as I keep my flashlight on, am I sending more energy? Well, yeah, in fact, you are. But you can't explain it with waves because waves are continuous. We have to explain it with something called quanta or packets of light. So this is the energy that's contained in a quantum of light. Now we're starting to treat light as if it were a particle. It's a packet. Right? That's the first indication that light didn't behave always as a wave. Even though we're using values that are associated with a wave, we're starting to make the transition and trying to understand light in terms of its packet behavior, its quantum behavior. Okay. Now, since we do have frequency here, and we also have the this equation, we'll put it over here, right? Remember this one. Right? Then the commonality here is this value right here. Okay? So suppose that you're given a problem and the question asks you, what's the energy of the photon? This quantum is also called a photon. Okay, that's the name of the packet of light, the photon. We can calculate its energy here, but what if you don't know the frequency? Say you know the wavelength instead. Well, you could take the wavelength, use the speed of light, find out what the frequency is, and put it in that formula. Or you can solve this one for frequency and substitute it in here. So now this equation becomes Planck's constant times C over lambda. Okay, and on that slide, we just put it together. Planck's constant times speed of light divided by wavelength is equal to the energy. And there's Planck's constant. This H equals, and I don't even have it memorized, 6.626 times 10 to the minus 34 joule seconds. And so it's a compound unit here, joule seconds. And that makes sense. If this is joule seconds, right, and this is hertz or reciprocal seconds, right, 1 over seconds, then the seconds cancel and leave us with joules, which is energy. Okay, I like to do dimensional analysis just to be sure that the equation is set up right. That makes sense. All right, so I might have to start this one manually.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also—
What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect.
Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions, so he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
There we go. The photoelectric effect. All right, their example in that little video, they used two cables and they shone light on one side and it made electrons jump to the other side. What we typically see today is that we would have a metal And then we would shine light at it with a certain energy. And it would eject electrons. That's the photoelectric effect. But the problem is that it only happens with light of a certain energy calculated with Planck's equation. If it's below a certain energy, in other words, if the frequency is too small, say it goes toward the red, and this metal responds to light only above a certain color and toward the blue, then how do you explain that? Because it should, if you shine any light, it should eventually eject electrons, but it won't. So that's another supporting argument for the packet theory, the quantum theory of light, or photons, the particulate behavior of light. All right, so here are the observations in black and white. I just described them. No electrons are emitted by a metal below a specific threshold frequency. So that V is supposed to be this one right here. That's the threshold frequency. It's got to be higher than that one or a little higher before you start seeing any electrons at all. So how would we measure that? Right? Electrically speaking, you would measure a current, right? A current is an expression in electricity for the movement of electrons over a period of time. So we get so many electrons expressed probably in coulombs. Coulombs per second would be our current of ejected electrons. Below that frequency, you don't get any electrons. All right. The ejection of these electrons by light that exceeds this threshold frequency produces increases as intensity increases. So it doesn't actually produce different electrons, it makes more of them. So intensity is like the light's brighter, but it's the same frequency, right? If you're shining blue light at the metal, all you need to do is just turn up the voltage on your source, and it will make a stronger light, but the same color. And that just produces more electrons. All right. Now, I'm not sure if they're going to tell us. Let me go to the next slide and see if it's part. Yeah, point 4 is if your frequency is greater than the threshold frequency, then you get the same number of electrons for the same intensity. But you get the same number of electrons, but now the extra energy that's contained in this frequency in excess of that value, you see that as kinetic energy. So if you exceed this value with your frequency, then you get your electrons, but they're also moving faster. So that extra energy that's contained in this frequency shows up as kinetic energy of the electrons. Okay, so what can we conclude from that? Well, the only explanation for that is that light is quantized. It arrives at the surface of the metal as packets or photons. And each one of those photons has to have this minimum energy. And one photon ejects one electron. And if the photon is more energetic, then it delivers enough energy to release the electron, and then the extra energy is translated into kinetic energy. So what does that say about the atoms? The atoms in that metal? It says that this photon, this minimum energy photon, is just enough to overcome the attraction of the electron to the atom. And so if you have an atom diagram here, and it's got its protons and maybe some neutrons, and then you have electrons out here, well, when that photon comes in, then it's got just enough energy. If this is the threshold frequency, it's got just enough energy to remove the electron from the atom. And that's what that says. Now, we don't lose the energy if the photon is less than the threshold. We don't lose the energy, right? It's either reflected and conserved, right? Or if it's absorbed by the metal, that energy is absorbed by the metal, it just makes the atoms and the electrons move, vibrate, right? It turns into thermal energy, right? That's why they're called thermal photons. They don't eject electrons. They don't have enough energy, but they do have enough energy to make the metal shake, right? We always have to conserve energy no matter what we do. We have to account for energy of all forms. When it comes in at a certain amount, it's either got to go out with the same amount, or if it stays put, we got to account for it somehow. Okay, and I've already mentioned this, that excess energy is translated into kinetic energy of the electrons. And that can be measured. Right? You can have a detector over here, and it will, oops, I can't even spell. This detector will measure the energy of impacting electrons. Don't ask me how they do it, but it's real. Intensity, though. Let me back up. There was one supposition when they only believed that light was a wave, that all you had to do was increase the intensity of light, and that would add more energy, and you could get those electrons off just by making the intensity more. Well, our understanding of intensity now is that intensity is actually a measure of photon density. How many photons per unit time are impacting the surface? Sometimes that's called flux. So it just means we're sending more photons of the same energy at the surface. And if it doesn't have this threshold frequency, then you're not going to get any electrons moving. What will happen? There's definitely more energy, right, impacting. If it's not up to this value, the metal gets hotter, right? You're adding more thermal photons, and the metal gets hotter. All right. So what does this photoelectric effect tell us about the structure of the atom? That's where it gets interesting. I sort of alluded to it there with that diagram. What it does tell us is that there is interaction between light and the electrons. Right? Because think about it. We know that an atom is composed of protons and maybe some neutrons and electrons out here. What does that light beam see first? Before it even gets to the nucleus, it sees electrons. It's got to get past the electrons. And so there is interaction between light and electrons. The absorption of a photon of light is specifically tuned to the movement of an electron from one energy level to the next. And there are no in-betweens. This is called quantization. Quanta means a unit of something. So if that light comes in and it's just the right amount of energy, and it has to be exactly the right amount of energy, then that electron will move from here to there. And in terms of an atom, the further away from the nucleus, the higher the energy of the electron. Because you have to add energy to move that negative away from that positive. It takes energy to do that. Okay. And we often call this concept, well, I'm not going to muddy that would muddy the waters. Forget what I was just going to say. There's no in between. This movement, if there's just enough energy, say, to get it here, it won't move. It's got to go from here to here only. If there's more energy and there's enough of it, it'll move to the next level or to the next level. And if there's enough energy, it'll move to infinity. It will leave the atom. But it's based upon the energy of individual packets, the photons. All right, that's not saying anything new. Except we didn't make this connection. If we're claiming that the electron moves to infinity and it's got more energy than the threshold, then what does that mean? That means that with kinetic energy, we know how to measure it and how to calculate it. If it's got more velocity, it's got more energy, that means it has to have mass. Electrons must have mass in order to have kinetic energy. Right? You may have seen in the news, maybe not recently, but over the past decade or so, efforts to find ways to propel satellites in space. Right? So one of the models that was used was the models of early 16th century explorers who crossed the oceans. Right? They did it in boats that had sails. They caught the wind and that drove the boat forward. Well, they're doing the same thing with satellites. There's some experimentation. They use huge sails made out of a very thin material called mylar. And it catches light striking them, in addition to other subatomic particles that are coming off the sun. And they build a pressure on that sail and they accelerate the satellite away from the sun. And it's all because light has mass. Right? When it impacts that sail, it delivers that energy due to its mass and its velocity to the sail, and that translates to an acceleration for the satellite. All right, there's my favorite picture of Albert Einstein. He was kind of elderly at this time, and he'd already made a name for himself, so it's okay to indulge his quirkiness. So along comes Albert Einstein. In 1905, he was actually working at the patent office in Bern, Switzerland. And he was a patent reviewer, right? He'd review patents to see if they were valid. And he'd get his work done in just a couple hours in the morning, and he'd spend the rest of the day working on his pet projects. And one of those was this special relativity theory. Well, he published it in 1905. And what it did was, and this was after he had published his paper on the photoelectric effect. Right? He'd already proved that. So he published this paper on special theory of relativity and proved mathematically that light has mass. So obviously he was a theoretical physicist. Now, there's a very fine distinction between rest mass and relativistic mass. Relativistic mass is the mass something has by its movement close to the speed of light, right? And for light, right, it's already there. So it has relativistic mass. Light wouldn't have rest mass because there's no such thing as light at rest, right? Light's moving or it's not at all. And he came up with this equation, right? That famous equation, E equals mc squared. So we've got three equations so far, right? We've got the speed of light is equal to wavelength times frequency. We've got energy equals Planck's constant times frequency. And now we have the equation or the equating of energy and mass. And the constant that is the multiplier is the speed of light squared. So what that tells you is a very small amount of mass. If we can convert that mass to energy, we get a huge amount of energy. Now, this was just theoretical, right? Everything was up here or on paper as he was writing it out. The experimental physicists were the ones who had to take his theories and either prove or disprove them. And Arthur Compton managed it took a couple of decades to get there, but he confirmed experimentally this E equals mc squared. And now why does that relate to the particle nature of light? It all goes back to the energy, kinetic energy of light. If light has kinetic energy, then it has to have mass. And with this E equals mc squared, Einstein was proving mathematically that light has mass. Mass can be converted into energy, light. And Arthur Compton then proved it experimentally. We don't have time to go into the details there, but it did happen. So the argument had been going on for decades and was well into the 20th century before people finally decided that, all right, we're just going to have to throw up our hands. Light can be a wave and it can be a particle. It's both. Well, the nice thing about that is, the fortunate thing about that, the realization that light can be a wave and a particle, is that matter can have wave nature as well as particle nature. So you can calculate a wave for me, only it's going to be a very long wavelength, very low energy, because I'm not moving. And if I'm moving, then I start to build shorter and shorter wavelengths or higher frequencies. There's an equation for it. Hopefully we'll get to it later. We'll either get to it in the slides or we'll get to it in review problems that we're going to look at maybe Thursday and next Tuesday. We're set up for reviews in those 2 days. Well, if we finish chapter 7 today, we'll get to review on Thursday. And we got plenty of time. So I do a lot of digressing when I have plenty of time. So which is correct? They're both correct. Light is both. Now, what are some evidences, characteristics of light that speak to its wave nature? Okay. I'll put this over here. Let me just keep them all together. The wave nature of light is demonstrated. One way that it's demonstrated is called diffraction. Now, our example here is a wave approaching a barrier that has a small hole in it. And notice when it strikes that hole, the hole serves as a point of origin for a new wave. That's why on the other side of this hole, instead of being a wave like this, now it's a point of origin and the wave goes like that. Right? Those black lines, consider those crests, and the white lines are troughs. Right? Diffraction. This is one example of diffraction. Another example is, say, if we have a barrier here and we shine light at it, if it's a wave, then what happens is it's blocked here, but as it exits this edge, it does that. So how would we know that it was doing this? Well, if light were only a particle, it would come to this thing, it would get stopped right there, but this would keep going like that. And we'd have a detector over here of some kind, and we'd see it here. But if we had our eye over here, there would be no light. We'd only see light up here if it traveled like a particle in a straight line. But in fact, we do see light down here. Right? So that process is called diffraction. The other characteristic of light that we observe, if we assume it's a wave, is called refraction. And don't get the two confused. Diffraction and refraction are two different processes. Refraction is speaks to a bending of light when it passes from one medium into another. So if we've got something here, this barrier, on this side we have air, and this side we have glass. Okay? Then when light comes in, which way does it bend? It bends this way. Right? So instead of going straight out like this, it bends. That's a product of the wave nature of light. Okay. Particle nature of light, however, is explained is used to explain the photoelectric effect. Waves cannot explain the photoelectric effect. All right. So we're inching our way closer to using light and the way that atoms interact with light to learn something about the internal structure of the atom. Let's talk about light spectrum. Right? A spectrum is a collection of wavelengths that describes the light beam that you're receiving. If it's a continuous spectrum, I don't even think I need this anymore. Computer's close enough. A continuous spectrum has all wavelengths. All wavelengths are represented. It's often called white light. Whereas a line spectrum has discrete, separate frequencies or wavelengths. A few or several wavelengths are contained in the line spectrum. Now, when you combine those into a single light beam, you might get a different color. Right? Anybody who's worked with in art, you know that when you combine certain color paints together, you get a different color. But that's just from the way we perceive those different lines in the spectrum meshed together in our eyeballs against our retinas, how we interpret them. But when we use an instrument to separate the lines of a spectrum, we see separate lines at different wavelengths. The simplest line spectrum is produced by hydrogen. And it makes sense. Hydrogen is the simplest element in the universe. It only has one proton, one electron, right? So you don't have interference from other electrons moving around, just that one electron. And what it does when it responds to light gives us information about the structure of that atom. All right. One of my favorite pictures. This was the cover art for Pink Floyd's Dark Side of the Moon. And they actually got it right. When white light shines on that prism, the light that's bent the most is blue light. The light that's bent the least is red light. So the spectrum is in the correct order.
The discharge tube is filled with hydrogen gas. When a high-voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra, due to the appearance of bright lines. In the hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
Okay. So we haven't explained what that n equals 1, n equals 2 means yet. When you look at an atom, in this case, we've got one proton and we've got one electron. But you can have 1, 2, 3, 4, 5 on up. These are all equal to n. So what they're saying is that the farther away you are from, let's see, they got 6 in there too, don't they? 6. The farther away you are from the atom, the higher the energy of the electron. So when the electron jumps back, say it goes from 6 down to 2, you get a quantum of light with a wavelength of 411 nanometers. Remember, the shorter the wavelength, the higher the frequency, and the higher the energy. So the blue end is the higher energy, the red end is the lower energy. So if we go from 6 down there, if we go from 5 to 2, right, we get energy at 434 nanometers. Right? So this is lower energy than that one. This is the highest energy. This is the next one. If we go from 4 to 2, and it gives off that energy at a wavelength of 486 nanometers. And if we go from 3 to 2, it gives off energy at 656 nanometers. We can calculate the energy of each one of these. All we need is to find out what the frequency is, or use that formula, right, that we devised for using wavelength with Planck's equation. Use that one. We also have to convert these to meters. You got to convert them to meters before you can plug them into your equation. But the transitions there are why we get the different colors. And this is supporting evidence, excuse me, this is supporting evidence for the quantum theory of light, the particle theory of light, because this only happens at those particular wavelengths. Now, if we shine light at a hydrogen atom at rest with this wavelength, it will promote that electron from the 2nd level to the 6th level. So it works both directions. Either you add the energy, or when the electron jumps down to a lower orbit, you get energy back. Okay. So to put it in black and white, the significance here is that only certain energies are allowed for the electron in the hydrogen atom to move. Now, at this point, we can only use the hydrogen atom to explain what's happening. Once you start getting polyelectronic atoms, where you have 2 or more electrons, then they start to interact, and it's more difficult to use this reasoning. Overall, the movement of electrons is responsive to certain wavelengths of light, but it's more difficult to actually calculate them if you have polyelectronic atoms. All right. Why is it significant that color emitted from the hydrogen emission spectrum is not white? Well, if the light emitted from the atom were white, that means it would be emitting all different wavelengths, and there would not be discrete levels for the electron to move. It can move anywhere. It can move here to here, here to here, here to here, here to there. It can move anywhere. That would explain white light, but we don't get white light from hydrogen. We get a line spectrum, and this is the explanation for the line spectrum. So now we've got an understanding of how the hydrogen atom is built with discrete energy levels for its electrons. I just answered that question already. Well, there we go again. All right. So for astronomers that are looking at stars, or even for scientists that are looking at phenomena in the laboratory, using devices that will split the light into wavelengths, we can investigate things that we want to know about the atom. If we know what atom it is, right, we get more information. If we don't know what it is, we can use these values that we obtain prior to the investigation that are characteristic of each element. Those emission spectra will tell us that we have this element in the sample. And I used to use that on a daily basis, identifying the elements in samples and how much of it is there in the sample. You can also use the intensity of light that comes off at that wavelength to determine how much of it there is. Okay, so now we come to using what we know so far and what Niels Bohr, the scientist that is responsible for the Bohr model, he knew all this stuff too. And he used it to devise this theory. Right? He tried to explain why atoms behave the way they do. This is the Bohr model. Niels Bohr, he was a Danish physicist. All right, what does the Bohr model say? Well, the Bohr model is only good for hydrogen or hydrogen-like elements. What do I mean by that? What I mean is that for hydrogen, right, with one proton and one electron, if we want to say something about helium, which has two protons and two electrons, we got to get rid of one of the electrons, right? So if it's got two protons, now we only want one electron. That means it has to be single charge, positive charge. That's hydrogen-like in electronic terms. Or lithium, we would have to have a 2+. It only leaves one electron behind. Then we can use the Bohr model to describe these various elements. All right, so what does the Bohr model say? Well, Bohr used a planetary model. He looked at the solar system and he saw the sun at the center, and he equated the sun with the nucleus of the atom. So he's got this nucleus at the center with one proton in it, like the sun. And then he had these orbitals out here. They got closer and closer together as you get farther from the atom. And those orbitals, those are where the electron stayed. At a certain amount of energy, this electron will stay here. A little more energy of the right amount, it'll go to here, into this orbital. Right? It's not correct, we know now, but it was a good start. These energy levels, he gave them numbers. 1, 2, 3, 4, 5, and on out. And these are N equals. Okay. So the N, this value, is related to the energy of the electron. The higher the number N, the higher the energy of the electron around this hydrogen atom. The ground state, you may see that referred to sometimes. The ground state is one in which the electron for hydrogen is at its lowest energy level. So it would be here. If you had an atom, say, of, I don't know, magnesium with 12, magnesium with 12, then it would have electrons here and they'd be stacked, and its ground state would be the lowest possible energy state. All the electrons are as close as they can get to the nucleus. And we'll explain the rules in a few minutes. That's the ground state. The lowest possible energy state under current conditions. And for our purposes here, standard temperature and pressure. Right, 25 degrees Celsius and 1 atmosphere pressure. All right. And there's an energy model. Right, so notice that the jump from 1 to 2 is a huge jump. 2 to 3 is a little shorter. 3 to 4 is even smaller. 4 to 5, they get smaller and smaller as you move further away. All right. Oh, what's missing? Oh, for the hydrogen atom, this only shows us 3 of them, right? We need an energy level 6 for the electron to jump from 6 to level 2, and that will give us the 411 nanometer value. These other 3 are accounted for. Here's another way to look at it, right? That central circle in the middle is, actually, it doesn't show us the nucleus. It only shows us the orbitals. So n equals 1 is the smallest circle in the middle. And then n equals 2 is the next one, 3, 4, 5. And that's how we explain the line spectrum, because of that quantum jump between levels. All right. So can we calculate the energy of electron for an energy level? Actually, we can. Bohr came up with this equation. Energy equals this constant minus 2.178 times 10 to the minus 18th times z squared over n squared. That's the energy for that electron in joules. Now, Z means exactly what it did when we were describing the structure of an atom, right? Z is, well, for hydrogen, 1, that's equal to Z, the number of protons. N is the energy level. Right? So in this case, Z would be 1, right? It'd be 1 squared. And then N would be a certain value, right? Let's say for the first energy level, this would be 1. Right, so 1 squared. So for n equals 1, the energy equals minus 2.178 times 10 to the minus 18 joules. All right, notice that as we, if we keep this one 1 for hydrogen, and we let this one go to say 2, and we divide this by 4, that means it gets less and less negative. That's because we add energy as we move up. And this value needs to get bigger, more positive. The more positive it is, the more energy is associated with that level. That's why those values are negative, because this way, as we divide them by bigger and bigger numbers, divide by 4, divide by 9, divide by 16, divide by 25, divide by 36, right? It gets smaller and smaller and smaller until eventually, what would it take for the energy to drop to 0? It would take infinity, right? If n were equal to infinity, then anything divided by infinity is 0. Right? Then energy would be 0, and the electron would be out here free at an energy level of infinity. That's typically what we call that is ionization. Right? We've removed the electron from the atom. But as long as it resides in one of these energy levels, it will have a numerical value. It'll be a negative value, but it's numerical. Okay. Let's see. Right. For hydrogen, this has to be 1, or a hydrogen-like. Well, actually, a hydrogen-like, this can change. For helium, that would be 2. For lithium, it'd be 3. But it would have to be a charged species. It would have to be helium +1 or lithium +3, +2. For 1 electron to remain behind, and then this would change depending on the element. So how do we calculate the transition? How much energy is required? Say we wanted to promote this from 1 to 2. Like, actually, we're going to add energy to it and move that electron up to the second level. Well, remember, when we're doing our calorimetry calculations, change in temperature is final minus initial. So the final energy minus the initial energy would be the transition energy. So we would take the energy calculated for 2 minus the energy calculated for 1. And that would be the amount of energy that was added to the system, which would be a positive value, right? It's just like before, system versus surroundings. The system would be adding a certain amount. If the electron moved from here to here, right, then this would be the final. This would be the initial, and the value would be negative. In that case, it would give up energy, right? So energy would be leaving the system, and it would be a negative value. That's one of the reasons why this equation is set up as negative here, so that we get those results, right, based on our system surroundings concept. All right, so let's see, do we have an example? Yeah. So this is what it would look like if we had it separated. And if you actually given energy for the final, for the 2, we just gave you the joule, or gave you the joule, then all you'd have to do is subtract the initial from the final. And you get a value. But if all you have is the n value, then you've got to go in and calculate it. But we can simplify this equation, I think. Yeah. We can simplify it. We can factor out that constant. And then we can put in our value for the number of protons, the Z number. What for the hydrogen atom transition from N5 here down to 2, right? What's that energy of transition? Well, we know it's, right, for hydrogen, it's 434, right? We've measured it. So does it agree with our calculation? Well, if we use those values, right, it's going from here to here. So final is 2 and initial is 5. That's why those 2 and 5 are in the place they are. Then we calculate. Then we calculate the change in energy and we get this many joules. Well, how do we relate that to the wavelength? Well, we got this one right here. Right there. That's a constant. That's a constant. We got this energy value in joules, and we just solve for lambda. Solve for the wavelength. Oops. Sorry. There we go. So that's what this equation is doing. And as it turns out, this, well, okay. Here what we've done is we've taken the wavelength, 434 nanometers, right down here, right there. And, excuse me. And in meters, we plugged it into the equation and calculated the energy. And notice the energy calculation comes out really, really close in either of the 2 versions. So that's confirmation that we're on the right track with the Bohr model. But like I said before, I hope, is that the Bohr model only works for hydrogen or hydrogen-like elements. And that was one of its greatest shortcomings. All right. So the Bohr model does correctly fit the quantized energy levels for hydrogen atoms and postulates only certain allowed circular orbits for electrons. Just that's its planetary model. So as the electron becomes more tightly bound, its energy becomes more negative. That is, it becomes less and less. Right? The closer you get to the nucleus, the lower your energy. And as an electron drops closer to the nucleus, it gives off energy. All right, we always have to conserve energy. If it's got a certain amount of energy way out here, when it gets close to the nucleus, it's less energy. Where does that energy go? It's emitted as light. Okay, we now know that Bohr's model is incorrect. First of all, it only works for hydrogen or hydrogen-like atoms. And it also postulates that electrons move around the nucleus in circular orbits. And we know that doesn't happen either. All right. So the color of light for each one of these is based upon that line spectrum, right? This one's violet, this one's blue, green, and orange, orange-red. So this one says, let's see, what was the question? What color of light is emitted when an electron falls from, oh, okay. I think I'm missing the statement in here. Which one is the lowest energy transition? The lowest energy transition is the shortest distance that the electron has to move. And that's from N3 to N2. N6 to N2 is a greater distance, so it's higher energy. So the lower energy, the longer wavelength, is N3 to N2, which is the more red. Okay, I got those backwards. That animation should have the question first and then the box. All right. Now we've got the problem that's developing with physics and chemistry at this time is that things are getting really small. Right? And up to this point, up to the beginning of the 20th century, classical Newtonian mechanics was sufficient to describe virtually everything. But now we're getting really, really small. And what we're finding is that it's difficult to predict everything about things that are that small in terms of where they are or how much energy they have, how fast they're moving. It's difficult. And it wasn't until Werner Heisenberg proposed his uncertainty principle that we started to get a handle and understanding. I mean, it didn't solve the problem per se, but it did alert us to the fact that there was uncertainty in our measurements, and it quantified the uncertainty. Right. So in this equation, which says changes in x times changes in, and that's velocity. Mass times velocity is momentum. It's often written like this with the Greek letter rho, is greater than or equal to pi, oh, excuse me, pi's on the bottom. Planck's constant divided by 4 pi. This is a very simplified version of Heisenberg's mathematics. Right? So I didn't want to get too deep into it, but this does illustrate the fact that this refers to position. Right? Where is it? This refers to speed or energy for that matter. So if we're just talking about a single particle, right, the mass is not going to change. So we're really looking at how fast is it moving. And this is where is it, right? Can we detect a change in position? Well, when we multiply these two together, change in position, change in speed, then it must be greater than or equal to Planck's constant divided by 4 pi. That just means as our certainty for the velocity increases, right? This is an inverse relationship. If this increases, then this has to decrease. In other words, if we know how fast it's moving, if we know its energy, then at this level, at this size level, we don't know where it is. We can only speak in probabilistic terms, like this is the region where it should be. Or if we say, okay, I've got it fixed in position, we know nothing about its energy. In general, chemists opt for this one. They want to be certain about the energy. And they're okay with statistics telling them roughly where the position might be. That's how it works in chemistry. Now, there were certainly other people that were working on this problem at the time. Max Planck, right? He was working on it. Albert Einstein was working on it. A Frenchman, de Broglie, he was working on it. We're going to look at de Broglie in a minute, either here, or we might look at it in the review document. De Broglie, when I talked about I have a wavelength, de Broglie proposed the equation that calculated that. Schrodinger. Schrodinger is a principal player in the burgeoning science of quantum mechanics. How do you deal with things at this level, this small level? And Schrodinger was central. His equations, the wave function that he proposed, helped us deal with things at this level and say something about their energies. Max Born was another. Paul Dirac was a Frenchman who was involved in it. Wolfgang Pauli and many others. Okay, so it's a combined effort, which is most of science. Modern science is like it makes an advance, and then other people come along and stack on top of it, or they discover that we got to do something with this one because it was wrong. So it's an effort over decades and centuries with lots of people involved. Now, Schrodinger came up with these wave functions, and they have this one interesting symbol. This is called psi. Right? And if you go to a college campus, a four-year college or university, and you drive down sorority and fraternity row, you'll see Greek letters plastered on the sides of buildings that look like houses. These are where those sororities and fraternities are located. They're in those places. And they're identified by their Greek letters. And so you'll probably find one that has this symbol on it, psi something something, or something psi something. But that's not what I'm talking about here. I'm talking about the mathematics. This function, when we square that function, what that tells us is, well, it's an indicator of the probability of finding an electron in a particular region of space. This is called the psi function. So here we are again, we're talking probability. When we say an electron is in a certain region, then we're basing it upon these equations. All right. If you haven't realized it yet, that's not the same as the Bohr model. Right? The Bohr model says these electrons are orbiting in this particle is in a circular orbit, just like a planet, right? But Schrodinger's equation says, no, they're not, right? Now, why do we believe him and not Bohr? Because Bohr's model explains very little. It only explains basic energy levels. We need to know more. And the developing quantum mechanics, theory of quantum mechanics, is where we're headed. That explains the behavior of electrons more completely for all atoms. All right. So here's an example. If we have a wave function that is the very simplest, This would be for a hydrogen atom. The probability of finding an electron in that region can be represented in two different ways, right? The top one is like a blue color. The more blue it is, the darker it is, the higher the probability of finding an electron in that region. Now, that's not in the nucleus, right? In fact, this probability distribution is in error. It should be more like this, right? If we have the probability here and the distance from the nucleus, then it should actually start here. If this is the nucleus, then it should start here and maybe go and then like that and tail off. Because the electron's not going to be right at the nucleus. Other distributions, that's a better one. Yes, this is much better. Okay. Let me look at my hard copy and get an idea of where we're headed, so I can make a coherent argument here. Okay. The size of the orbit, which we're calling the orbit, is that region of space where we're likely to find the electron. It's very difficult to define that. That's one of the hallmarks of quantum mechanics, is it's based on probabilities. The orbital itself is a wave function. In other words, so it's a mathematical expression. We don't actually see it. Right? There's no way to see it because you can't fix the position of the electron. I mean, if you could, then you'd alter it. That's another paradox, right? As soon as you observe something, you have altered it at this size. So we picture the orbitals as three-dimensional density maps, right? As where we're more likely to find the electron in this region than others. So the radius of this orbital around the hydrogen atom, say this is the nucleus, and then this region here, the spherical region in 3 dimensions, would be denser right in here and be less dense out here. Okay. That region predicts that the electron will be found in here 90% of the time. You're 90% certain that it's in that region, right? You can't be absolutely certain. All right. But as strange as this may seem, as improbable as it may seem, this theory actually helps us understand atoms better than the Bohr model. I know it's hard to accept that right now, but it's true. So how are we going to describe an individual electron in a position around the atom in terms that can be calculated using quantum mechanics? Quantum mechanics requires that we have 4 numbers. 4 numbers, unique numbers for each electron around an atom will describe its characteristics, right? And there are several. All right, so let's define those. One of them is already given to us, right? N, that's the principal. Yeah. The principal. Want to spell it right. Principal. The principal quantum number. And what the principal quantum number tells us is two things: size and energy. So we're using Bohr's model as a jumping off point, because in Bohr's model, the principal quantum number did address this idea of energy. But it also tells us size. So the bigger the n, the bigger the region that we have to consider for the location of the electron. Okay, now what numbers can we assign? The numbers that can be assigned here are just like the Bohr model. They start at 1 and they keep going up to whatever size n you want. Okay, that's the principal quantum number. The angular momentum quantum number, or L, let's see, angular momentum quantum number gives us information about the shape of the orbital. Okay, it could be spherical, it could have lobes on it, it could be a donut. There are various possibilities, and these are all mathematically generated. So one thing to understand as we proceed, these are stacked numbers. In other words, for each one of these, you can have a certain number of these inside each one. So if we have any one of these, it could be here, 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 or here. Or if we have one of these, it could have several of those possibilities. Now, it's like a tree branching out. Okay, what numbers can we have here? Well, the numbers here are based upon that number. Starts at 0, and it goes 1, 2, up to n minus 1. So it's based upon this one. Example, say we had n equals 4. At that level, n equals 4, we could have 0, 1, 2, or 3. N equals 1, 3. We could have 4 levels of L inside that n equals 4. All right. Then we have m sub L. M sub L is the magnetic quantum number. Magnetic quantum number. This tells us orientation in three-dimensional space. Okay? And the possibilities it can have are based upon one of these numbers, right? We're stacking them. We're branching out from this level to this level to this level. So what can this one be? This one would be minus L minus L plus 1 on up to 0, and then L plus 1 on up to whatever. So if we had this angular momentum were 2, then this value would be minus 2, minus 1, 0, plus 1, plus 2. Up to plus, excuse me. That's not right. Yeah, it's minus 2, then add 1 to it is minus 1, then add 2 to it is 0, and add 3 to it, then it would be a plus 1. So it goes from minus L to plus L by whole number increments. That's a better way to say it. Okay. The last one M sub S is the spin quantum number, electron spin quantum number. Okay, this one's easy. It's either a +1/2 or a -1/2. So at each one of these levels, whatever the case may be, each one of these levels, you can have an electron at +1/2 or -1/2. So at each one of these, you can have 2 electrons. All right. Those are the 4 quantum numbers. And these quantum numbers mean something to people that work in this area. All right, those 4 quantum numbers, they stick it in their equations and they come out with predictions of size, energy, shape, orientation, and spin. That's what it says. All right. So let me erase these so I don't have to erase those. It's 2:30. What do we have? We have till 3 something, don't we? Yeah, 3:50. Okay, I got a little over an hour left. Let's see, can I make it? Maybe. If I don't finish, then I can pick it up on Thursday. Okay, so what is this table? This table comes straight out of your textbook, or at least my edition of the textbook. It may look a little bit different in your edition. What we're looking at here are the possibilities for principal quantum number, angular, magnetic, and spin. Actually, it stops here. For the first 4 principal quantum numbers. Okay? So what we're saying is, if the principal quantum number is 1, then the only possibility is 0 for L. And the only possibility of 0 here is 0 there. Okay? So if this is 1, you've only got 1 sublevel available. And we're speaking of hydrogen, actually. That's hydrogen. Okay, one thing I didn't mention up to this point is when we start writing out electronic configurations for atoms, if we try to use numbers only, it can get pretty messy. So what we've done is we've substituted letters for this level in here. Right? So if the value is 0, we give it an S. If the value is 1, we give it a P. If the value is 2, we give it a D. If the value is 3, we give it an F. And unless your electrons are excited for all the ground states, F is as far as we need to go. And I'll explain that to you later in terms of the periodic table, actually. So if we wrote N equals 1, L equals 0, N equals 1, L equals 0, then we would use that designation. And since it can only have one of these, then that's as far as we need to go. But if it can only have one of these, how many electrons can it have there? It can have 2. So we can have 2 electrons here, and we would write that like this. Except, if this is hydrogen, it's only got 1 electron. So that is the electronic configuration for hydrogen. It's N equals 1, L equals S, magnetic is 0, and it only has 1 electron in it. All right. Now, when we get to this one, how many magnetic levels can you have for that one? -1, 0, and +1. So if we went and we couldn't have this one if this were true. You can't have it there, right? That's what that table is showing you. N must be 2 in order to have access to 1 or P. So it would have to be a 2 P to have how many levels? Sublevels of 3. It would have a minus, it would have, 1. It would have -1, 0, and +1. So underneath here, we would have -1, 0, and +1. Then how many electrons can we have there? Well, we can have 2 in each. So a maximum of 6. Right? More detail later. Okay. So let's move on and actually get some experience here. For principal quantum level, N equals 3. So if we're looking at this one, 3, determine the number of allowed subshells, different values of L. Right, this is a shell. Some authors refer to them in these terms. This is a subshell. And this one is an orbital in common language. Okay, so if we have a 3 for the principal quantum number, how many allowable L's can we have, subshells? Well, if we've got 3, what's the possibilities here? Well, we're going to start with 0, 1, and 2. Right? So you can have 3 you can have 3 subshells at N equals 3. All right. Okay. Oh, did it say what are they? Oh, and give the designation of each. All right. So for each one of these, this is an S, this is a P, and that's a D. There we go. So if we wrote it, we would have to say this part first, then the other part. So it would be a 3S, we'd have a 3P, and a 3D. All right. What if we have L equals 2? So now we're going to focus on this one right here. L equals 2. How many determine the magnetic quantum numbers, M sub L, and the number of orbitals? Well, if this is 2, that means we start at -2. And then we go to -1, then 0, and then +1, and then +2. So we have 5. 5 possibilities there. All right, so 5 orbitals. How many electrons, a maximum, can we have here? Well, each one of these can have a +1 or a -1. So we can actually have 10 electrons. That doesn't mean we do. That just means that's allowed, a total of 10. All right. What we're trying to do here is to show a representation or several representations of the s orbitals. So we're looking at these right here, those orbitals, right? We're talking about shape. The shape of these orbitals is spherical, but it's not a solid sphere, except for the 1s. 1s is a solid sphere. 2s actually has one node in it. What's a node? A node is a region of space, for our purposes, a region of space where we expect the probability of finding an electron to be 0. We calculate no probability of finding an electron in that region. So for 2s, we've actually got a sphere within a sphere. We got this sphere out here, and then as we get closer, we find a dead space, no probability. And then we start again with the inner sphere. 3s has 2 nodes. right? So similar, we have 3 shells, including the solid sphere in the center, and 2 nodes separating those 3 spheres. Now, for our shape, if we went to p orbitals, we find that p orbitals have sort of a dumbbell shape. Okay? And the p orbitals, if we take, let's make some space here. P orbitals, right? A p orbital has a value of 1, L equals 1. Okay? So, if L equals 1, how many magnetic quantum numbers can you have? Well, -1, 0, and +1. This tells you orientation. The p orbitals are the easiest for me to understand, because if you have an XYZ coordinate system, right, X, Y, and then Z going back into the board, then one of these, I don't know which, the negative one would be like this, the positive one, the 0 might be like that, and then the other one would be like this. So that orientation is on axis, that XYZ axis. It gets really complicated when you get up to D's. And remember, these are calculated. These are computer-driven solutions to the Schrodinger equations. And in this case, we have 5 possibilities, right? And doesn't that make sense? If for D, then this is 2. That can be -2, -1, 0, +1, and +2. So that's 5. 5 of them. And there they are, the 5 orientations in space. They look a lot like the P's, right? The dumbbell shaped, but their orientation is different. And then you get that last one. It's got sort of a dumbbell and a donut. All right, and F is just completely wild. If F is 3, right? F subshell is L equals 3, and we got -3, -2, -1, 0, +1, +2, and +3. That's 7. So you need 7 different orientations to accommodate the different shapes. And that's what we see there. Right? You're not going to have to regurgitate any of that stuff. If you want to work on any one to remember, go to the p orbitals. Right? Those are on axis. There are only 3 of them. And that'll cover most of the stuff we're going to do this semester. Okay. Electron spin, of course, is +1/2, -1/2. So each one of these here can have 2 electrons in it. That means 14 electrons here, maximum. The Pauli exclusion principle. We saw his name a little bit earlier. The Pauli exclusion principle simply says that in any atom, no 2 electrons can have exactly the same set of 4 quantum numbers. They can have the same N, L, M, but they'd have to have 2 different spins. Or they could have different L's and the same everywhere else. But they have to be a unique set of 4 numbers. Okay. So what's the problem with polyelectronic atoms? Well, that's most of the periodic table. In fact, all but one. Right? Hydrogen excluded. The rest are polyatomic. And polyelectronic atoms. The problem is that when you get more than one electron in reasonably close proximity, you get the repulsive effects. We don't know how these electrons are moving. Right? We chose to focus in on energy and these four quantum states. We're not saying a whole lot about actually where they are. We're saying this is the region that we'll find them. So we can't say with any certainty what type of repulsive forces are being experienced by any one electron, again, with its neighbors. We can't calculate them exactly. But we can say other things. One is when electrons go in, as we add protons, right? As we increase the number of protons, and for each proton we add another electron, because we're working from neutral atoms first. So as we add a positive, we need a negative. So we have a number of electrons out here somewhere. As we do that, we know that for any one of these, we know that the electrons prefer to go in lowest energy first. And if this one's occupied, we move up. But also down here, as we enter an S, if that one's filled, then we have to go to the P. If that one's filled and it's available, we go to the D. So we fill in that order also. So we do know that much about how electrons enter the atoms as we start to build them with more and more protons. Now, what we would expect is this, right? The 1 or the 2 or the 3 give you a general idea of the energy of the electrons. Notice they're not exact. But this is the way they would be. The P is a higher energy than an S. And the D is a higher energy than the P by just a little bit. When you start putting electrons into them, then those energies shift because of those electron interactions, and also the effect of the number of protons on them. So this is the starting point. We'll talk about where that takes us in the future. But first, I want to talk about this concept called the penetration effect. And this is not a concept that that is akin to, say, the murderer penetrated the victim's body with a knife to a depth of 6 inches. It's only vaguely resembling that. Penetration effect is still, we have to deal with probabilities. So what we're saying is that, for example, a 2s electron penetrates to the nucleus more than one in the 2p orbital. That is, when we look at the probability distribution of a 2s electron, the biggest spike in the energy for the 2s is out here, and the biggest spike for the p orbital is actually at a lower energy. But the 2s also has, remember, it has a node, so it drops to 0 and then it comes back up closer to the nucleus. So it penetrates some of its electron density closer to the nucleus. And that gives the overall energy signature of the 2s orbital lower than the 2p. And that's due to the penetration effect. What that does is it causes the electron that's in that orbital, the 2s orbital, to be attracted more strongly than the electron in the 2p orbital, because the p orbital can't get that close under any circumstances to the nucleus. Let's see, I think I've got a drawing here. There we go. So if we look at this drawing where the probability of finding an electron is on the y-axis and the distance from the nucleus is on the x-axis, then you notice that the p orbital has one hump closer than the big hump for the s orbital. But the s orbital penetrates closer to the nucleus with that small hump, and that gives it lower energy. That's what we mean by penetration. When we say the 2s electron penetrates closer to the nucleus than the 2p. And in general, say if this is an example of a 3s orbital, it's got two nodes, but it also penetrates with the two lobes closer to the nucleus than, say, a 3p. Right? So there's a 3s, 3p, and 3d in diagram, and you notice that the 3s has penetration here and here. The 3p is the big lump is closer than the 3s, but it only penetrates down here, whereas the 3s penetrates even closer. And of course, the 3d has its big hump closer than either of them, but it doesn't penetrate at all toward the nucleus. So that explains why the 3s is a lower energy than the 3p, which is a lower energy than the 3d. All right. Now what we're going to do is take a look at the periodic table. Okay. First, a little historical background. What we're talking about here is patterns. Patterns in element behavior. They were first recognized that we have records of by Johann Dobereiner. I think he was German. In the late 18th century or the early 19th century. What he found was triads, in other words, groups of three elements that had similar behavior. And we use here as our example the halogens, right? Chlorine, bromine, iodine. They behave similarly in chemical reactions. They're not exact, but they're similar. And there were other triads that he developed, but that's as far as he went. He just identified them and let it go. Then along came Julius Lothar Meyer. We'll talk about Mendeleev in a second. Meyer conceived of a periodic arrangement of elements. Well, I guess we need to introduce Mendeleev too. Mendeleev was working in Russia. Meyer was working in Germany, and they both had similar concepts about the periodic arrangement of elements. Okay, when we talk about periodic arrangement, if we look at the periodic table, right, I'm going to draw out a rough diagram here. Let's see, like this, down here like this, across here like this, up like that, like that. Okay. Groups are vertically oriented. Elements in the group have similar behaviors, at least on this side and on this side. It gets kind of squirrely in here. But they noticed that these groups only lined up when, as we're adding elements by increasing the number of protons and electrons. When we're adding them from left to right, then we get out here, and if we put one out here, it looks like this group over here, right? So we don't need to go any further. We just circle back, as they say, circle back and put it down here in the next period. So we got periods here and here and here. So that's what's known as a period. We go to the end, and then instead of hanging off the end of the falling off the edge of the earth, we circle back and put it in this one. Now it's in its correct group. And the only way we can do that is if we use this idea of the period. It's derived from physics, periodic motion. Right? If any of you have had physics, you'll know that periodic motion is still motion, but it doesn't go anywhere. It's like a pendulum on a clock. Right? Weight down here, and it moves backwards and forwards. Right? If it goes up and back and here, that's one period. So we've gone down here and we've gone back here again. That's one period. All right. So Meyer and Mendeleev conceived of this idea of periodic arrangement of the elements in order to maintain their groups. But Mendeleev is given more credit for his arrangement and his version of the periodic table for a very significant reason. What Mendeleev did was, if he found a position in here where the next element that we knew of, that had been identified, would be here, but it didn't fit with the group. So instead, he moved it over to the next one, which is usually where it would behave like that group. And he left blanks in his table. And not only did he have blanks in his table, but he predicted the physical and chemical characteristics, elements that would go in that position. He said, one day, somebody's going to find that element and it's going to fit that hole. And his predictions came true. That's why Mendeleev gets credit for the periodic table more so than Meyer does, because he used the periodic table to predict the existence of undiscovered elements. Now, the periodic table is arranged with groups, vertical groups, and horizontal periods. And increasing atomic numbers, or numbers of protons, from left to right, top to bottom. Now, I left out these two down here. Okay. We can also subdivide the periodic table into these 2 columns here and these 6 columns here. Those two together are known as representative elements. These are known as transition elements. Of course, you probably already know a lot of this stuff, because if you did the extra credit, then you had to fill these things in. These are alkali metals. These are alkaline earths, or alkaline earth metals. Okay. These are halogens. Well, these are noble gases. These are halogens. These are chalcogens. Right? These next group are pnicogens. The chalcogens start with oxygen, the pnicogens start with nitrogen, halogens start with fluorine, and the noble gases start with helium. And that's all we have. Down here are lanthanides and actinides. Okay, and these two fit right in here. Okay, that's a general outlay for the periodic table. Now, the numbers, the group numbers here, they're using the old system in this slide. So lots of times they have Roman numeral 1A, 2A, 3A, and so forth. Go all the way over to 8A. When you get down here, we use B's. Or you can just number them from 1 to 18 all the way across. Actually, this old system gives us a little more information. All right. Metals versus non-metals. And if we start here, right, with boron and aluminum, draw a line there, and then zigzag elements like that. Then we're subdividing the table into metals and non-metals. So metals are over here, and non-metals are over here, which means that most of the table is metals, very few non-metals. But there are a special group very close to this dividing line that are called metalloids. And that's because depending on the chemical environment and the reaction, sometimes they behave like metals and sometimes they behave like non-metals. Those are metalloids. Probably the most useful one, as far as we're concerned, is silicon, because all of our electronic technology is based upon silicon. That's why they call it Silicon Valley out there outside of San Francisco, where they do all computer stuff. All right. Now, we need to learn how to build atoms. First is the Aufbau principle. All it says is, as you add protons and 1 electron each for each proton you add, as you're building atoms successively, building elements, the electrons always go into the next available lowest energy orbital. So if we were to write the electronic configuration for oxygen, which has 8 electrons. Remember, N equals 1. N can be 1, 2, 3, on up. L can be 0 up to N minus 1. And then M sub L can be, M sub L can be anything from minus L to plus L. Okay? So, if we have N equals 1, which would be the lowest energy N number, what does it have available? Right? If it's 1, then it can only be 0. That's it. You're done. N minus 1 is 0. So, and 0 is S, P, D, F, 1, 2, 3. So that's where we start, 1s. Right? Then we can put 2 electrons in here, right? Because plus 1/2, minus 1/2. Then we can go to the next 2, right? 2 can have an S, but now 2 can have a 0 or a 1, 0 or 1. So it can be 2s and 2p, right? Again, we can only put 2 in this one, plus 1/2, minus 1/2. So we've used 4 of them already. We need 4 more, right? How many can you put in a p? Well, p is 1, and we can have minus 1, 0, and plus 1. So you can have 3 orbitals in that subshell. Okay? That means that you can have 2, 4, 6. You can have a total of 6 electrons. We only need 4. Right? So we can put all 4 electrons in that p orbital. So that would be the electronic configuration for oxygen. All right. Hund's rule is another one. The Aufbau principle, and then Hund's rule says that when we go to this orbital level, the lowest energy configuration is one with the greatest number of unpaired electrons. When you pair electrons, they get close together and they repel one another, which increases the energy level. So you want to decrease the energy level as far as possible. So if we were to put those four into these three levels, then we would put one with a spin up. That's how I say plus or minus, spin up or spin down. Then we put the next one in this orbital, not paired. Then we put the next one in that orbital, not paired. We got one more electron. It has to be paired. There's no option. So that would be the orbital assignment for these electrons. 2 paired and 2 unpaired. All right. That obeys Hund's rule. And that's what it would look like. The authors of these slides like boxes and double-headed arrows. I like lines and single-headed arrows. It's quicker. All right. What do we mean by valence electrons? Valence electrons are those electrons in the highest energy level for the atom. So they would have the same principal quantum number, and it would be the highest principal quantum number available in the configuration. So in this case, we've got 4 and 2. We have 6 valence electrons. Okay. This also corresponds to the group number in our old system. Remember when we had Roman numeral 1A, 2A, and then 3A, all the way over to 8A. Okay. So with 6 valence electrons, oxygen should be in 6A. Okay, that's why this old system is so useful, because the numbering system tells you how many valence electrons are in that atom. And there's our example. All right, so that's 6A right up here. That's where oxygen would be, right there. Here's what we're also showing from the periodic table. As you're adding electrons, notice that this one is hydrogen right here. It only has one S. Right? This one is helium, right? It's kind of out of place. We put it over there because it belongs with the noble gases, but we're filling a 1s orbital over here. So it can have 2 electrons. Now, once we get past that little glitch, each one of these in these 2 columns, the alkaline metals and the alkaline earths, they're filling s orbitals. Right? Once you get those s orbitals filled, you're done. Now, it could be s orbitals here, it could be s orbitals there or there. It's still filling s orbitals. On this side, these 6, you're filling p orbitals. Notice that there are 6 groups. How many electrons maximum can you have in p orbitals? 6. Because there are 3 sublevels, right? -1, 0, +1, 2 electrons each, 6 electrons, 6 groups. S orbitals, you can only have a +1/2 and a -1/2 spin, so you can only have 2 groups. That's why you only have 2 columns here for the s orbitals. D orbitals. Right? D orbitals have 2. Right? So 2, if D equals 2, how about, what's the M sub L? It can be -2, -1, 0, +1, +2, right? 5 orbitals with 2 electrons each, 10 electrons, right? So as we're building, we can have 10 protons with each have an electron. So if we're filling d orbitals, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the structure of the periodic table is built around the orbitals that are being filled in the outermost shell. And then f orbitals down here, right? If f equals 3, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. That's 7 orbitals with 2 each is 14. And if you count your squares, the lanthanides have 4 here, actinides have 4 there. It's 14, excuse me, 14 there, 14 there. Okay? So now we're getting an idea. We can use the periodic table to build atoms because of the way it's organized. All right, this little device is one way that we can use to be sure that we get those orbitals in the correct energy level. Notice, let's see. Notice that this filling order right here. So we line them up, n equals 1, 2 through 7, right? 1s, we can only have an s orbital there. N equals 2, we can have an s and a p. N equals 3, we can have spd, right? 0, 1, 2, 3, 0, 1, 2. 4, we can have 0, 1, 2, or 3, f. And 5, we only go to f, so we stopped across there. And then we write in the possible orbitals and how many electrons they can have. And then we take a diagonal, this 45-degree diagonal, and we can fill, we do 1s first, 2s next, 2p next, 3s next, 3p next. And then instead of going to 3d, this is where that polyelectronic interference comes from. The energy level for 4s is lower than 3d. So we go down to 4s and back to 3d. So if we wrote out the possible configuration, we'd have 1s, 2s, 2p, 3s, 3p, and then 4s, and then back to 3d. And this device will keep you in the right energy order. Right? Where do we go from 3D? Well, we go back to 4P, right? 4S, 4P. And then we go to 5S. And then we circle back to 4D. And then we get 5P. So it kind of gets messy in there, doesn't it? And then 6S, and so on. But that's the energy level as we increase energy levels. And we know from previous examples, you can only have 2 here, 3 there, 3 orbitals here, 6 electrons, 2, 6, 2, 10. We don't have any F's yet. Okay, this is one way to do it. The other way is to use the periodic table. We're going to draw those things. Okay, let's go back to the periodic table. Notice that as we build 3s, then we go to 3p, and then we go back to 4s before we get to 3d, 4s. Then we get to 3d in our first, in this period, the 4th period has 3ds in it. Then we go back to 4p. Then we can fill with 5s, 4d, 5p. So as you progress left to right, top to bottom, you go through this same sequence in the periodic table. So if you know the periodic table structure, you don't have to remember that. It'll tell you. All right, so let's take an example here, sulfur. Sulfur. So we look at how many protons and electrons does sulfur have? Looks like 16, right? Okay, we know only 2 here and 2 there. That's 4. 6 here, that's 10. We got 6 more to go. 2 there. I got 4 more to go. 4 there. Okay? Notice that we don't need the rest of these. That's it. Notice also What was oxygen? Remember oxygen? 1s2, 2s2, 2p4. Notice for the outermost orbital, the p orbitals, we have 4 for oxygen, and we have 4 in the 3p orbital for sulfur. And they're in the same group, oxygen, sulfur. Okay, that's why they have similar behavior. They have similar orbitals, and they have the same number of valence electrons, 6. Okay. This also shows you a shorthand method. Notice that if we go from here to here, that's the same as neon, right? 2, 4, 10. So in order to simplify this, we say neon, and then we pick it up after that, 3s2 and 3p4. And that would be a shorthand version of the electronic configuration for sulfur. Why do we use neon? Because neon has completely filled orbitals. Right? That's full, full, full. And these guys are the valence. So when we use this method, we go back until we back up till we're below, start to get below the valence shell. And then everything back here is the same as a noble gas. All right, how about barium? All right, let me erase this, that. And let's clean these up. All right, let's do barium. Barium is a big atom. Barium has 56. All right. So 2, 2, 6, 2, 6, 2, 10, 6, and 2. See how many we got so far? 2, 4, 10, and then 2, 4, 10, and then 10, right? And then 8. How many is that? 38. So 38 from this one is 16, right? No, 18, excuse me, 18. Yeah, 18. So I need 18 more. That's 10, 6, and 2. All right. That would be barium. But notice that this is the valence. It only has 2 valence electrons. Right? In the second column, all the members of the second column, the alkaline earths, have 2 valence electrons. That's why when they ionize, they prefer a 2+ charge. Right? We learned that early on. This is why. And then this part, we take the periodic table and we back up. We back up from barium to cesium to xenon. And this one represents xenon 54. Then we tack on this part, and that's also barium. That gives us the information we need. We only need to know that it has 2 valence electrons to predict its behavior. Europium. Europium is 63, and it has f orbitals in it. Right? I'm not going to mess with f orbitals. This is just for illustration purposes. What you find is that europium is a lanthanide. So what it has is the xenon base, plus it has the barium 6s2, but then you get down into the f orbital filling, and you got 7 f electrons. All right. Let's see if I can manage this. All right, we're going to look at some periodic trends in the tables, in the periodic table. We're going to have to define what they are: ionization energy, electron affinity, and atomic radius. And these definitions are critical. Say we have an atom or an element, and we want to find out how much energy does it take to remove one electron, right? Send it to infinity. How much energy does it take? Well, what we don't want is to put energy into the element just to get it to change a phase, right? Go from solid to liquid or liquid to gas. So that's why we start with a ground state atom in the gaseous state, right? It's not ionized, but it's gaseous because now, from now on, the energy we put in goes into the electron, not into phase changes. Then what do we get? Well, if we remove one electron, we get a single positively charged gas. That's the expression for any ionization energy. Now, this will be the first ionization energy, where we remove one electron from the neutral ground state atom. You can also do a second ionization energy if we take this one right here and remove another electron, if it's available. And this will have an enthalpy for it. This will have an enthalpy for it, right? Each one. Well, they give it an I. That's okay. What this slide also shows you is that when you remove one electron, it takes a certain amount of energy per mole. When you try to remove the second electron, you're trying to remove an electron from a positively charged nucleus, from a positive balanced atom. So it's more difficult to separate a negative from a positive when it's in this state. So this would be higher energy. This would be less energy than delta H2. And this would be less energy than delta H3. In this case, for magnesium, notice that the energy required for the second ionization is twice what it was for the first. Right? And that's a fair trend. But where do those electrons come from? Magnesium has 3s. Magnesium, let's see, 12. And it would be neon, 10, and then 3s2. So if we remove those two electrons, right, they take a certain amount of energy, but these are the valence electrons. If you try to remove a third electron, you're getting down into what we call the core, into this noble gas configuration. When you try to move an electron from a core, then the energy required goes way up. And that's what we're showing here. It goes from 1,400 to 7,000 kilojoules per mole to make that third electron, because now it's coming from here. All right. So in general, the trends for our periodic table are that from left to right in a period, the first ionization energy increases. So we get an increase in ionization energy from left to right. Why is that? Well, notice we're in the same period. Principal quantum number is 1, 2, 3, 4. You're adding more protons and you're adding electrons to that principal quantum level. So you're not moving the electrons significantly farther away. What you're doing is increasing the nuclear charge. You're making more positive charges in here. So the outermost electron is feeling a stronger pull. And in fact, it'll shrink the atom. So that means that the first ionization energy, as we go from left to right, increases because of that increasing nuclear charge. As we go from top to bottom, the ionization energy decreases. Why is that? Well, even though we're adding protons to the nucleus and increasing the nuclear charge, we're also adding electrons to higher energy levels. So the outermost electrons are further away, plus they've got all these electrons in between shielding them from the nuclear charge. So that shielding effect decreases the amount of energy required to remove the outermost electron. All right, so when we combine the trend, we would increase this direction and increase that direction. So the trend is from lower left to upper right is increase. First ionization energy. Okay. If we go across the periods, what we notice that in general, we get an increasing ionization energy, but there are some anomalies in there. Right, when we go from, say, beryllium to boron, beryllium is losing electrons from the s orbital, whereas boron is losing electrons from the p orbital. The p orbitals are further out, right? They're lower, they're actually higher energy. So it takes less energy to remove a p orbital than it does an s orbital electron. So as we go from beryllium here to boron there, now you're removing that first electron from a p orbital. It takes a little bit less energy. Not much, but it's measurable. Also, when you go from nitrogen to oxygen, you get a decrease in energy required for the first ionization energy for oxygen. The best way to explain that is to look at their electronic configurations. Let's put nitrogen first. Nitrogen is 7, oxygen is 8. So we have a 1s2, 2s2, 2p3, 3, 4, 5, 6, 7. And then oxygen is 2, 2p4. Okay, the way to understand this one is if you have a drop in first ionization energy here, the electron that's being removed must be at a slightly higher energy because it takes less to get it away from the atom. Okay, these guys don't tell us anything right here because they're paired like that, like that, like that, like that. But when you get to P, you've got these 3 orbitals, and nitrogen has 3 unpaired electrons, but they're separated from each other. Whereas oxygen has 4. That electron right there is in the same orbital as the other electron, even though they're opposite spins, but they're still pushing on each other. There's a repulsion there. And that slight repulsion allows you to remove that electron with less energy. That's why we get that dip from nitrogen to oxygen. And you can see that trend across, it shows up occasionally. Once you start getting into the transition elements, like down in here, right here, and here, then you have different explanations for those. And we're not going to get into them just yet. Okay. Explain why the graph of ionization energy versus atomic number across a row is not linear. Where are the exceptions? Electron repulsions is a major factor, and difference in orbital energies. I left that one out. Electron repulsions is good for nitrogen, oxygen, but from beryllium to boron, is a difference in orbital energies. All right. Which would require more energy to remove an electron? Sodium or chlorine? Well, let's look at our periodic table. Right. Sodium and chlorine are in the third period, both of them. So the trend is from left to right, we increase the ionization energy. And so sodium should be lesser than chlorine. Chlorine would be the larger requirement for energy to remove that first electron. How about lithium and cesium? Well, lithium and cesium are in the same group. Cesium's way down here, lithium's way up here. It takes more energy to remove lithiums because the electrons are closer to the nucleus. Plus, cesium has a lot of electrons between the outermost electron and the nucleus, so there's shielding. So more energy would be required for lithium. Which has the larger second ionization energy? All right. So let's do this one. That's good. What are our choices? Lithium and beryllium. Lithium and beryllium. So lithium is going to be 1s1. Let's see. Lithium is 3, beryllium is 4. So 1s1, 1s2, 2s1, correct? And beryllium would be 1s2, 2s2. So the first ionization energies will be a little higher for beryllium, right? Because it's to the right of lithium. And it goes lithium, beryllium. The second ionization energy, this is the first ionization energy would remove that electron and make this a positive. The second one would remove that electron and make this a positive. Now, the second ionization energy, which one? The second ionization energy would get down into the core of lithium. But the second ionization for beryllium would still be in the valence. So this one would be second ionization energy higher value than beryllium. Okay? And this chart shows you that trend, right? The core electrons, you have to remove more electrons as you increase the atomic number. Then you got to remove more of them, more of those valence electrons before you get down into the core. But once you do, the core jumps way up. All right, electron affinity. The temptation, I better leave that there. The temptation for electron affinity, understanding electron affinity, is to think in terms of it's just the opposite of electron ionization, but it's not. Because what we're doing now, instead of removing an electron, we're adding an electron to the neutral atom. So we're starting with the gas again. We have to start with the gas, right? Because we can't let phase changes interfere with our energy calculations, our energy measurements. So we need to add an electron to this one. And what do we get? Well, we get a negatively charged gas, right? Okay. So when an electron comes from infinity down to the atom, what happens? It gives up energy, right? That's going to be a negative value because it's leading the atom. Okay? So the stronger the affinity of this neutral atom to that electron, the more negative that value is. So more negative means stronger affinity. Okay? Now, how about left to right? As we go across a period from left to right, the affinities become more negative. So let's see. Electron affinity, EA, actually increases from left to right. Well, actually, the value decreases. Decrease. what we're saying is more negative. But it's a stronger attraction, which means the value is more negative. Okay. And from, let's see, more negative, general. Down a group, it becomes more positive. More positive, which means less attraction. So EA down increases. Becomes a more positive value. Okay. So the trend from lower left to upper right is more negative. Right? Or an increasing affinity, which is measured as more negative value. All right. Now atomic radius. Atomic radius is not as easily defined as ionization energy or electron affinity. Atomic radius, we have to use several different types of techniques depending on the nature of the element. Typically, if we know the distance between the nuclei of two atoms of the same element, right, if we can measure that distance between those two, then we can just take half the value, right? And that gives us the atomic radius. Here we go. The problem is, right, what do you consider the outer limit of the atom? Right? Sometimes when they come together, they sort of squash a little closer, and that kind of skews the value. So atomic radius, the values that you may see reported in literature or in reference manuals are going to vary within a narrow range, but it depends on how they were determined as to whether they, how closely they agree. Basically, two types of radii are accepted. One is metallic radius. When you have a metal in a crystal structure, then sometimes it's reasonably easy to measure the spacing of in the structure with X-ray diffraction, usually. And that distance between two adjacent atoms then can be determined, and you can calculate the metallic radius. The covalent radius is usually determined as one has the distance between nuclei in a homonuclear diatomic molecule, such as hydrogen, right, or oxygen, or nitrogen. Those would be easy to get at. Others, covalence would be a little more troublesome, right, because not all nonmetals, which is where you're looking at covalence, and not all nonmetals form diatomic elements. Right? Some of them prefer 4. So you would have to force them into a diatomic situation in order to make that measurement. Or sulfur. Sulfur prefers that at room temperature and pressure. And so again, you'd have to separate it. You'd have to devise a way to reduce it to the diatomic. And you can use various methods: X-rays, electron crystallography, neutron diffraction, microwave spectroscopy, and others. So depending on the method you're using, you may get a different answer than some other laboratory. And usually when these values are reported, you're told in the descriptions actually how how it was determined, right? Was it a single determination using this method, or was it a composite? Is one of the problems. Okay, what are the trends then? Well, the trends vary, but if we're thinking of only the representative elements, right, the s orbitals filling and the p orbitals filling, it tends to behave fairly well. It's when you get into the transition elements that things kind of go up and down. But generally speaking, the atomic radius going across a period from left to right, the radius decreases. And the reason for that is you're putting protons and electrons together, increasingly from left to right. But the electrons are going in at the same energy level, so there's not much shielding. You're increasing the effective nuclear charge. So as you increase the nuclear charge, it tends to draw those electrons closer to it. So we're shrinking the atom as we go from left to right. Okay. As you go down a group, you tend to increase the atomic radius simply because the electrons are going into larger and larger orbital sizes, right? I mean, N refers to the energy and the size. So as you go down a group, you're adding electrons to a bigger size, and that makes the atom bigger. All right. Here's a representation of only the representative elements, right? So you'll notice that lithium, beryllium, well, we don't have to skip anything for those. We don't have to skip for that one. Potassium, calcium, yes. We do have to skip the transition elements in here. So by the time you get to this other side, they're already shrunk, right, way down. And notice that down, the s orbitals behave themselves pretty well. The p orbitals, they tend to behave reasonably well, increasing in size as you go down. All right. Which should be the larger atom, sodium or chlorine? Well, they're in the same period. Chlorine is further to the right, so it should be the smaller one. Sodium should be the larger one. Lithium and cesium. Right? Lithium and cesium are in the same group. Cesium is way down here. Lithium is way up here, so cesium should be the larger one. All right. Now, let's think about the orbitals themselves. Let's compare the 1s orbital for hydrogen and the 1s orbital for lithium. And just think about those orbitals. We know that lithium is 3. So lithium is going to be 1s2, 2s1. And this one's going to be only 1. But let's think about just these orbitals right here. Right? What size is the orbital going to be for this one versus that? Well, look at it this way. We've got 1 proton here. We've got 3 protons here. And we're adding electrons into this same orbit. So what we've got is a stronger nuclear charge drawing this 1s closer to it. So the larger orbital should be the hydrogen, 1s. Okay, we're not talking about the whole atom. We're just talking about that orbital. Once we start adding these out here, of course, it's going to be bigger because we're adding, to a larger space. How about which is the lower energy? Remember, energy is lowest the closer you get to the nucleus. So if the lithium is shrunk down smaller, then the 1s orbitals for lithium are going to be lower energy. They're smaller orbitals, but that makes them closer to the nucleus. So they're going to be lower energy. See, is that all for that slide? Yeah. All right. So let's arrange these elements, oxygen, fluorine, and sulfur, according to increasing ionization energy. So we got oxygen, fluorine, fluorine, and sulfur. All right, let's put them in relative position. Oxygen's here, fluorine's right next to it, and sulfur's below. That's easier to deal with ionization energy. So ionization energy is going to be increasing from left to right and from bottom to top. So if we're putting them in increasing order, the ionization energy should be, first ionization energy should be sulfur to oxygen to fluorine. All right. How about atomic size? Well, sulfur is going to be biggest. Right? Oops. Sulfur is going to be biggest. Right? And then fluorine is going to be smallest. And oxygen's in the middle. So it should go the opposite direction, fluorine, oxygen, sulfur. All right. Okay. Final thoughts on the periodic table. Let me see. Do I need to even talk about that? Okay. The number and type of valence electrons that primarily determine the atom's chemistry. That's why the groups, every member of the group has the same type of valence electrons and the same number of valence electrons. The electron configurations can be determined from the way the periodic table is organized. Right? We know that, and we're going to see some examples in your review questions. And when we talk about them, we can take Thursday and next Tuesday to do review. So come back on Thursday and we'll start the review, and we can take all the time we need. 3, certain groups in the periodic table have special names. Well, yeah, we know about that. Basic division of the elements in the periodic table is in metals and nonmetals. Yep, know about that too. What's the difference between metal and nonmetal? Right. Qualitatively, metals conduct heat, conduct electricity very well. They have a luster if they're polished. Right. They're all but one of them is solid. Right. Mercury is the only liquid at room temperature. Whereas nonmetals can be any phase, solid, liquid, or gas. They generally don't conduct electricity or heat very well. And let's see, there was a third one. When they're solid, they have very dull appearance. Okay. And that's it.